Today we're going to revisit the concept of the Cantor middle third set in the guise of what we've been doing recently. To remind you what we've been doing, let's first say that S is a subset of the real numbers. We'll say that a point in S is an isolated point if there exists a positive epsilon 0 such that the intersection V sub epsilon 0 of P with S is just the singleton set consisting of P. In other words, we'll say that P is an isolated point if there exists a neighborhood of P whose only point in S is P itself. We'll denote I parentheses S as the collection of isolated points of S. We'll say that S is a discrete set if every point P in S is an isolated point. That is, I of S equals S. We'll say that a point P in the real numbers is a limit point for S if, given any positive epsilon, we can find an element x sub epsilon in the intersection V sub B of P with S, and x sub epsilon does not equal to P. Please note that we do not require that P be an element of the set S. Sometimes we'll call a limit point a cluster point for S or an accumulation point for S. We'll denote L parentheses S as the collection of limit points of S. Note that S is contained in I of S union L of S. That is, every point of S is either an isolated point or a limit point. Moreover, the intersection of I of S and L of S is the empty set. That is, there are no points that are both isolated and limit points. Next, L of S is contained in S. That is, every limit point of S is also a point of S, if and only if every Cauchy sequence contained in S has a limit also contained in S. As examples of this, let's consider the open interval from A to B, or even the closed interval from A to B. Then I of S is the empty set, that is, there are no isolated points in these intervals, and L of S is the closed interval from A to B. You'll notice that L of S contains some points not in S if S is the open interval. Let's recall a couple more definitions. Again, say that S is a subset of the real numbers. The interior of S, denoted by S circle, is the set of points in S such that there exists a positive epsilon, such that V sub epsilon of P is contained in S. In other words, this is the collection of points such that there is some neighborhood surrounding that point that is completely contained in S. Next, we'll say that S is closed if L of S is contained in S. That is, every limit point of S is also a point in S. More generally, the closure of S is the set S bar, which is S union with L of S. That is, we'll add in the limit points of S if we need to form S bar. The complement of S is the set SC, which is the set of those real numbers x such that x is not an element of S. We have a theorem that explains the properties of these three. First, the interior S circle is an open set. Next, the closure S bar is a closed set. Next, S is closed if and only if its complement SC is open. Similarly, S is open if and only if its complement SC is closed. We have a few more properties about closed sets. First, the closed interval from A to B is an example of a closed set. Next, let's say that we have a set S sub lambda, where lambda are elements from some indexing set capital lambda. This is an arbitrary family of closed sets. If this is the case, then the intersection is also a closed set. Similarly, let's say that we have a finite collection of closed sets. That is, our indexing set capital lambda is just a finite set. Then the union is also a closed set. Let's use all of this to make some observations about the Cantor middle third set. First, let's do a quick recap of how we defined this set. Remember that we start with the unit interval from 0 to 1. Our first step is that we'll remove the middle 1/3 of this set. This gives now two closed intervals, the first from 0 to 1/3, and the second from 2/3 to 1. As our next step, we're going to remove the relative middle thirds of this set. This means that our two intervals now get broken into four intervals, namely the interval from 0 to 1/9, then the interval from 2/9 to 1/3, then the interval from 2/3 to 7/9, and finally the interval from 8/9 to 1. The picture that we have looks something like this. At the very top, you can see C0. This is the unit interval from 0 to 1. Just below that, we have C sub 1. This was the collection of the two intervals, the interval from 0 to 1/3 and the interval from 2/3 to 1. Just below that, we then have the set C sub 2. This was the collection of the four intervals, from 0 to 1/9, 2/9 to 1/3, 2/3 to 7/9, and 8/9 to 1. We continue in this way so that C3 now has 8 intervals, C4 has 16 intervals, and so on and so forth. Continuing in this fashion, we now have a sequence of subsets, C sub 0, C sub 1, so on and so forth, defined recursively in the way that you see here on your screen. We proved before that the limit, that is the intersection over all of these, is a set where we can express the elements x in the set in terms of ternary expansions, some as k goes from 1 to infinity a sub k over 3 to the k, where the numerators a sub k are either 0 or 2. We proved that this set C is an uncountable set. This subset of the real numbers is called the Cantor middle third set, and elements of the set are called Cantor numbers. We're going to prove a special result today. That is that the Cantor middle third set is a closed set with no isolated points. We could have also called this a perfect set. In general, a subset S is said to be perfect if I of S is the empty set, that is, S contains no isolated points, and L of S equals S, that is, S is a closed set. Let's discuss the proof of this. First, let's show that the Cantor middle third set has no isolated points. Let's pick a point C, which is a Cantor number. For any positive epsilon, we can choose an n such that epsilon is greater than 1/3 to the n. We're going to pick a very special element x sub epsilon based on the choice of p. Well, because p is a Cantor number, we know that it has a ternary expansion, a sum k goes from 1 to infinity, a sub k over 3 to the k, where the numerators a sub k are either 0 or 2. Let's choose our new number, which will actually be another Cantor number, x sub epsilon, where the first n elements in our ternary expansion look the same. However, the remaining ones we're going to choose by flipping a sub k. So for example, for p, if a sub k is 0, then for x sub epsilon, we'll choose to have a 2. If for p, a sub k is 2, we'll choose for x sub epsilon a 0. So again, we have a ternary expansion where the first n terms in the sum look the same as the first n terms of the sum for p, but all of the remaining ones get flipped. Wherever there was a 0 for p, there's now a 2 for x sub epsilon. If this is the case, we can now consider the absolute value of x sub epsilon minus p. Here we have a geometric sum, and if we work everything out, then we find 1 over 3 to the n, which is less than epsilon. In other words, we found an element x sub epsilon that is in the intersection b sub epsilon of p with c, yet x sub epsilon does not equal p. This means that we can always find another Cantor number that is arbitrarily close to any given Cantor number p, but this new Cantor number x sub epsilon is different from p. This explicitly shows that any Cantor number p is not an isolated point. Next, we want to show that L of c is c. That is, every limit point of the Cantor number is a Cantor number. And actually, every Cantor number is the limit of some Cantor number. Well, we know that the collection of Cantor numbers is contained in the union I of c with L of c, and we just proved that I of c is the empty set, so we know that c is contained in L of c. It suffices then to show that L of c is contained in c if we'd like to show equality. Let's say maybe there is some number p that is in L of c, but it is not a Cantor number. We're going to prove that this can't happen. Well, since c is contained in the closed interval from 0 to 1, we know that the limit points have to also be the closed interval from 0 to 1, so our point p has to be in this closed interval. But this means that we can express our p in some ternary expansion, some b sub k over 3 to the k, where the numerators b sub k are either 0, 1, or 2. Now, the numerators b sub k are not all equal to either 0 or 2, else we would have that p is a Cantor number. This means that there is some numerator, maybe call it b sub n, which has to equal 1. Based on this n, let's choose an epsilon to be 1 over 3 to the n. Here's where we're going to form our contradiction. Since p is a limit point, this means that there exists some x sub epsilon in the intersection v sub epsilon p with c. So let's write x sub epsilon as a sum here, so that our x sub epsilon minus p will be this sum, absolute value a sub k minus b sub k, divided by 3 to the k. Now, when k equals n, remember that b sub n equals 1. However, a sub n is either 0 or 2. Well, if a sub n is 0, then 0 minus 1 is 1. But if a sub n is 2, 2 minus 1 is also 1. So this means that the absolute value a sub n minus b sub n is always 1. So no matter what in this sum, there is always at least one term where we have to have a non-zero numerator. This means that our absolute value, x sub epsilon minus p, is greater than or equal to 1 over 3 to the n, which of course is equal to epsilon. But this contradicts the assumption that x sub epsilon is an element of v sub epsilon of p, which is the same thing as saying that the absolute value, x sub epsilon minus p, is less than epsilon. Since we have here a contradiction, we see that our original assumption that p is not a Cantor number must have been false. This means that every element in our limit set, L of c, must be a Cantor number. Thanks very much for watching.